Alright, we're going to look at diffraction now. Diffraction is something we do cover in year 11, but as usual, you may not have done year 11. Diffraction and interference are part of the same phenomenon. What we're looking at is what happens with waves. Now, when waves hit a gap or the edge of an object, the wave is represented at all points in that gap, right? And what we're saying, and this is Huygens' principle, not mine, and what he basically said was a wave is being generated all the time by the particles in it. And those particles have an effect in all directions. So this particle is going to affect things that way, this one that way. And so particles or waves should bend round objects with no problem, all right? And they do. But what happens is that the next wave that comes along, right? So this wave then comes along. He does the same thing, and we can get some interference. There's another little video I've done on what actually happens, but if the wavelength is very, very small, then the other wave that comes up catches up, because normally what would happen is we'd expect there to be this curved effect after the wave travels through, because I said they can go at an angle when they come out of that gap. So what happens is when they've got a really small wavelength, the next wave catches up quite quickly and it sends out its little guys, and we get this interference that we talked about taking place. And so we get a lot of destructive interference out here. And so instead what we end up with when we've got a small wavelength compared to the size of the gap, what we end up with is we've got our gap, we've got our small waves. They generally tend to come through pretty much unaffected with just a slight amount of bending on the ends. Now what happened was they were out here, but the other little guys caught up and there was destructive interference. So it's not perfectly flat out here, but basically the wave effect has disappeared. Now, if we've got, again, the same size gap, but much bigger wavelengths, these are wavelengths, right? Then what tends to happen is it goes out in all directions. But this other one doesn't catch up in time to create interference. So therefore, you have much more curvature when the wavelength, it was the same size gap if you like, when the wavelength was comparable in size to the gap. So this is the big issue, is when the wavelength is comparable in size to the gap, the following waves don't have time to destructively interfere, and you get much more bending round the gap. And this is what we call diffraction. It's an interference effect or a non-interference effect resulting in a lot more of that bending. Now, a few things to consider is wavelength and gap size. And gap size. If the wavelength and gap size are comparable, lots of bending. So for example, if I shine a torchlight along here, and this is 1 meter, the torchlight should, when it gets to the edge, go down there, right? With diffraction. But it doesn't, because this is a big object and a wavelength of light is 1/2000th of a millimeter. That's very tiny compared to the size of this object. So there's very little bending and the light just tends to go along and hit the wall. So the amount of bending depends on that. Whereas a sound wave that's coming along, if I transmit a sound wave along here, and it has a wavelength of 60 centimeters, it's going to bend around here, no problem, because it's comparable in size. By the time the next bit comes along, it's not going to be able to cancel out, and you're going to get plenty of sound around the corner of a 1 meter bench. All right. So wavelength and gap size, very important, and that's diffraction. Now, what you get is, or what we look at, is a few different effects. We can do it with gaps, 2 gaps, and because the waves bend through these gaps, they go out in different directions, right? They go straight, they go like that. Now what's going to happen in the middle here is, and this is the important thing to remember, is phase. Phase, what does it mean? Phase, all these parts on a wave front, this is a wave front, are in phase. That means this peak is at a peak. It's like the peak of a wave that you can surf. And 40 meters along, it's also at a peak. It's not in a trough. So the wave is continuous. It's all in phase. So the wave hits these gaps in phase. The wave is in phase. A crest is in that gap at the same time a crest is in that gap. A trough is in that gap at the same time a trough is in that gap. Then they travel through these gaps off in different directions. If they've traveled the same distance and same speed, they're still going to be in phase. So in the middle here, we're going to get constructive interference. Now what's going to happen just a little bit further up, around about there, for example? This one travels that distance, this one travels this distance. If that one has traveled further, which it has, and if it's traveled half a wavelength further, they started in phase, crest at the same time as crest, now they're half a wavelength out. We'll get what we call destructive interference. And that's because they are half a wavelength out of phase. They are out of phase. What does that mean? Let's see if we can just clarify that a little bit better. That means, and what do I mean by half a wavelength? We draw our wave. These two waves are in phase. And when they hit each other, their amplitudes get twice as big, their troughs get twice as big. If I now draw a wave half a wavelength out, these two guys are 180 degrees out of phase, or half a wavelength out of phase, or 180 degrees out of phase. If these two guys combine at a single point, at that point, when this one is negative, this one is positive, principle of superposition, they cancel. So at that point, we've got destructive interference. So what we'll get when we come back to this diagram here is, at this point, constructive interference, twice the amplitude. At this point, we've got destructive interference, which is they cancel out. At this point, we've got, again, one wavelength difference, so there's constructive interference. I'll put this on another piece of paper. So when you've got two waves coming through a gap, look here, what you're going to get, I won't draw the waves, but what you're going to get is you'll get constructive interference there, then destructive, constructive, destructive. So it's constructive, destructive, constructive, destructive, constructive. So this one is no wavelength difference, half a wavelength difference, one wavelength difference, 3/2 wavelength difference, two wavelength differences. So when it's whole wavelength differences, they're in phase, and we get constructive interference, destructive when they're half a wavelength difference. So what you'll tend to have is you'll have a line upon which the waves would all be bigger than usual. You'd have another line like that here, where again the waves are all bigger than usual, and another line like that where they're all bigger than usual. And in the between, you've got these areas where you've got that destructive interference. So these are sometimes called maximums. the destructive interference line minimums. With light, they're often called fringes. So you could have a bright fringe, dark fringe, bright fringe, dark fringe, bright fringe. And it's all to do with constructive and destructive interference. And we'll have a similar pattern over here. One of the next videos will discuss what happens if this is light and it's white light, because light has blue, green, and red, and they have different wavelengths, so they actually have to travel different distances before you get that constructive interference. So this is diffraction, which is really a interference phenomenon.